5 had one objective in mind, and this is the objective. It's all about finding zeros of polynomial function or polynomial functions. And I should mention again, real zeros end up being the x-intercepts. We're going to put that over here. The real zeros, real number zeros are x-intercepts, the x-coordinate of the x-intercepts. Okay, so you're given some polynomial function. So you're given a polynomial function. F of x is equal to some. I'll just make it up over here. I'm not going to solve this one, but in generally what I'm going to do. So I might have, say, 3x cubed minus 2x squared plus 4x minus 1. And what we'd like to do is be able to find all the zeros of that and then write it in some factored form. We'd like to be able to rewrite this, maybe with some coefficient out front, probably not. It could be just multiplied within. We'd like to write it in some way of having all the different factors of that, raised to whatever they are. In this case, they all have to be for the first power because it's a third degree, so we're looking for 3 zeros. They could be repeated or something like that. So our objective is going to be to take any polynomial and find its zeros and then write it in factored form in some way, shape, or form. What tools do we have to analyze that? So the tools we have are as follows. First tool we have is we have the fundamental theorem of algebra that we just presented. That tells us when we find something, what else? For example, if I found, one of these to be a imaginary root, if I did there, I know I have the complex conjugates. One was a radical, I know I have the radical conjugate. So we have that tool to use. We also have the long division tool. We're going to employ that to divide things out and get us back to a manageable thing, which is the other tool we have, and that is essentially your quadratic formula. Quadratic formula for factoring. Sometimes you can factor the quadratics directly, or you can use the quadratic formula to factor them, or factor quadratics. So we're going to be using that skill. We need one other tool. Now, in the old days, the other tools that we use, I'll put these in different colors down here. I'll call this is, 5. They use something called the rational zeros theorem. And but sometimes they would actually use log division. They would use something called synthetic division. These were all very useful tools years ago, before we had what we're going to be using is a technology. And the technology we're going to use is either your graphing calculator. I prefer, we can use Desmos. You can use GeoGebra, or your graphing calculator. I prefer to use this instead of these. These are complicated, very complicated things here. This is not complicated. It was a nice tool years ago to evaluate a function, but now that we have technology, these don't give you any real insight into anything. They're great. This rational zero theorem is a great theorem and very innovative. They needed it, 100 years ago. Otherwise, they would never find these zeros. But today, we plug everything in a calculator, and we can get estimates or sometimes the exact values of zeros, which then allow us to take something like this and rewrite it in a fact form. It's kind of an amazing thing that we can do that. And let me show you what I mean in the couple minutes we have left. Now this one may not work for 3. Yeah, let me see if negative. That's not going to work. I just made this one up. Now it doesn't work for all of them. The rational zeros doesn't work. We are not going to cover them in this course. I should put that as a disclaimer. That's why I put them in a different color. Their level of importance has dwindled over the years, in my opinion. They're taught in most of the pre-calculus courses, but you never use them in calculus. Sometimes they'll do it, but you're just going to use your technology. Your technology will kind of show you right away what this would show you with a lot of work. This will show it to you in seconds. This might take you minutes to go through and check everything. And that's why these things don't really do anything better than technology, but there's a lot more work involved. And that's what it's going to be the goal of here, finding the zeros and then writing it in factored form. Let's put this one in and see if we can estimate anything. This one we may not be able to. So it doesn't work, and this would also be true of the rational zeros here. Technology doesn't give us anything less than we would normally get with those other theoretical approaches. So let me go and get us going over here. So one of the first things we will start with, and this is where you can use your graphing calculators and stuff like that, is plotting out those functions. So we might have here something, and we'll put that one in for now. I'm going to go over this all straightforward on Monday when we have more time. I just wanted to give you a quick view. So here you have 3x cubed. I'm going to put it as y. It knows already, but I'll put it as a y equal to that. Minus 2x squared plus 4x, or x, excuse me, minus 1. Okay, so what we see here, this one only has one real zero. If you kind of zoom out, this is a typical graph of a cubic. It has one real zero. And if we come over here, that's why I like using tools such as Desmos. We can get a nice estimate of that. That's at 0.272. Now, sometimes if you put that into a calculator, we can actually get the actual fraction. But here with Desmos, it's a little bit harder because it always estimates or rounds it to the nearest, if you will, thousandths place. So it's not always perfect. We're going to see some other ones. On the test, I gave you some more exact ones. But you could actually test and see if that is a zero exactly. Meaning, I could put 0.272. So there's my f. Let's see if it works. Let's try it out over here. So I take 3 times, 0.272. Let's see how close we get. Cubed. Minus 2 times 0.272 squared plus 4 times 0.272. So it's not exact, minus 1. So you can see over here, it's not exact. So they did some rounding. So in this case, we will not be able to analyze this function as we would like. If this had turned out to be exactly 0, maybe if we take it out to a couple more decimal places, this might be where your calculators would actually be more appropriate. And we can plug this in. Let me show you, because you'll be doing a lot of that on your calculator. Let's see if we can find that as well. Let's come over here. We don't have much time left, but I'll try it anyway. I'll plug that same thing in. Let's clear that out. Oh, I'll put it over here. So I have my 3x cubed minus 2. Whoops, doesn't like that one, so I have to use. Oh, I have to go backwards over here. I thought I could do an x on my thing, but it doesn't like the x. 2x squared plus 4x minus 1. And we can graph this and we'll get the same picture that we just got there. Which we should. Here we go. Oh, I must have missed something. 3x cubed. Did I miss something? Minus 2. Unless minus 2x squared. Oh, so maybe it does. I didn't think it should. It should give us the same exact picture. What happened here? When I have times over here, let me just put a times in. Put something here. No. It's strange it's not looking the same. Let's go back over here into this, and what did I do? 3x cubed minus, that's a typo here by me. It's hard to see, and I'm surprised it didn't balk at this. That's a change of sign. That's not subtraction. So there it is. I accidentally put a change of sign in there, and I'm surprised it didn't catch that. Now I graph it. Now it will look more like the other one. Yeah. So you have to be careful what you enter in here. So that's where it is more precise now. Because this is the change of sign, and I needed a subtraction. I just hit it by mistake. I might have done, I probably hit the minus sign on my keyboard, and that's what messed it up. Okay, what we can do is we can find the zeros of that. So we can go over here and look for the calculator portion, and let's find a zero value. So what does it do? It wants a left bound, so we're to the left of that 0, you hit enter. Then you got to move it to the right side of that, hit enter. This will give me a little more accuracy, I think. So that's what they get, 2.718873.8. So we got 2.272. This gives us a little more accuracy. Still not going to be enough. There is no repeating pattern over here. So we don't know that fraction that much. Okay, so we're out of time. So the only homework I want to give you right now is just to read over 5.5. We will be going over that in greater detail on Monday. So just read that over. No other homework. And then we're going to show how to use all these different tools to then take different functions that we can analyze. It doesn't work for everything. There's a prime example. We could estimate the zeros, and that might help, and then we could play around and do it. But the zero could be something like, something crazy. That's why we can't do it. It could be, x is equal to, 237 over, 800 or 896 or something, or 98. And it may be hard to find that particular, if you will, fraction. But for us, just so we can do these things, and in the calculus, most of the times you'll see that we choose functions so you can analyze this. This one is unanalyzable in that regard. But we do know, and we can estimate it's one real zero. The other zeros we know are going to be complex. So these are going to have i's in them. And we know that for a fact too, and we'll talk about that. So just the graph does tell us something. Okay, so that's all we have for today, and then we will meet back here on Monday. So the only homework is to read over 2.5 and see if you have any questions in that, and work over those sort of problems. Don't do the homework yet. Read through it, and then we'll go through it again step by step. And then I'll repeat some of those things, and then we'll show how to analyze it, because I have 2 days built in for 5.5. Today was just a brief introduction because I knew we just had to be going over the homework. I just wanted to get a very brief introduction, but we'll really hit it on Monday. Any questions? Okay, so everyone stay safe, have a good weekend, stay healthy. We will see you all on Monday. And everyone's hopefully doing okay, they're healthy. But the crux of this whole chapter is all about finding, zeros of polynomials or polynomial functions. And along the way, we introduced a lot of different things. We have to work with complex numbers. We also have to practice how to do long division. And then we hit upon the fundamental theorem of algebra, which is kind of tells us how to find all the zeros of polynomials, but finding, how to put them in factored form. And they can either factor into a series of linear binomial factors with sometimes, and potentially more often than not, these irreducible quadratics. Those are when you have complex zeros or when your roots are radicals. If they occur in that way, then you can't just write them. You can, but it's a little bit harder to write them as a factor of a linear factor, a binomial factor. You can do it, but instead you might have a complex number or some radicals in there. It looks a little cumbersome. But today we're going to look at that whole process of what we do. And we're going to rely a lot on technology. What we're not going to be using is Descartes' rule of signs, rational zero theorem, which is sometimes put in a course like this. They were very good, 100 years ago. They were indispensable before calculators, before devices were available for being able to look at these functions and try and decipher what the zeros are. But now we're going to let technology take over for us for a little bit, and then still use that to use our analytical skills to then take that function, whatever it might be, and put it in factored form. The overall objective is to take a polynomial and put it in factored form. So in here, kind of our end objective, in addition to finding those zeros, is to put a polynomial function in factored form. So let's kind of jump right into it. I'm going to look at the even problems. I'll assign you the odd ones for that'll be due on Wednesday, for tonight and Wednesday. Let's take a look at some examples. I'll go through them, and then I'll have you try some. Here's my function, f of x, and I'm going to look at, this is number 2 from our chapter exercises, x cubed plus 6x squared plus 5x minus 12. Now what we're going to do is we're going to graph this. Now sometimes if you're really good, like I'm looking at this and I can see that in this case, looks like -1, no, not quite. We'll take a look at this. If I put in 1, -1, yeah, not quite. Let's put this into Desmos. You can put this into your calculator on the test. I'm going to use Desmos because it's a little bit easier to see. That's be my first step. I want to find the zeros. So I'm testing. I know there's at least one real zero. How do I know there's one real zero? Because we have that kind of theorem that says if this is an odd exponent, I will cross over the x-axis. It doesn't matter. If it's odd, I cross. If it's even, it may or may not. But since this is odd, I know there's at least one real zero. So let's see if I can find it, see if it's a simple rational zero that I can work with. So let's plug that into our Desmos and kind of work it from there. Let me open up the window over here. I'll share the screen with you. So here's our Desmos. We're just going to put in, y equal to x cubed plus 6x squared plus 5x minus 12. Oop. Down. There we go. So looking over here, it looks like we have a couple of potential real zeros over here. This one over here, we can see this one right here is x is equal to 1. If I just click on that, that's my real zero. This looks like -3, and that looks like -4. And we can validate this, but this is an easy one. So if I just use Desmos, I can validate that this is just the real zeros are -3, -4, and +1. Let me go back to what we had over here. So from that, we could actually make it easy on ourselves, and the real zeros are x is equal to -4, x is equal to -3, and x is equal to a +1. That means each of these is associated with a binomial factor. This is associated with the factor x plus 4. This is associated with the factor x plus 3, because if I set it equal to 0, I get -4. Set it equal to 0, I get -3, and this is x minus 1. So in this one, I could have went right away to rewriting this in its factored form as x minus 4 times x plus x plus 4 times x plus 3 times x minus 1. Now let's say, for example, I only discovered that 1 was a 0. Maybe I only saw this one being a 0. What could I do? We're going to see a few in a minute, but I'll just kind of do an easy one. Well, what I could do is I could remove this factor from that polynomial. And this is how I do long division. This is what we employ long division for. So we would then, if I said that's a factor, that means x minus 1 is a 0. So I take my x minus 1 and divide that into this cubic polynomial function. And I go through the process. Okay, so I look at what do I need to multiply this by to get an x cubed, and that be an x squared. To do that, I get x cubed minus 6x squared, x squared. Give me a wake. I would be subtracting over here, so that becomes 0. That becomes a 7x squared. Bring down the 5x. Then I multiply that by 7x, so I get 7x squared minus 7x. Subtracting, I would get plus 12x and bring down the negative 12, and then I just put 12. And now I get 12x minus 12, so when I subtract it, I get a 0 remainder. Anytime you get a 0 remainder, that means it's a factor. So this also factors into the x minus 1, and what remains is x squared plus 7x plus 12. Now, once we get it down to a trinomial, well, we know how to factor that. So I could go and continue. So, if I didn't notice these right away, I could then say, oh, can I factor this trinomial? So I put an x and an x, and then I'm back to my algebra skills. Two numbers that multiply to 12 and add up to 7. Well, 4 and 3, plus 4, plus 3, and I'm back to that. So that's one of the ways of doing it. This one was a little bit easier because we could see them all as their real number counterparts. Okay, let's take a look at another one so you can see how I am approaching the whole process. It's very systematic, and I'm using the fundamental theorem of algebra. It's a third-degree polynomial. I'm looking for 3 solutions, and here they are. They could be all real. One of them has to be real. I know one of them has to be real, and it has to be because it's cubic, it has to cross the real axis. If it's not an odd exponent for the leading term, then it's a little bit different. But the fundamental theorem of algebra tells us all the little nuances of polynomial functions that help us to pull it all together. Okay, let's move to another one. Now I'm going to move to number 4. I'm doing right out of the text the homework problems. So then we get f of x is 2x to the 4th r. Now I'm not guaranteed to have a real solution. I may, but I may not. Minus 10x cubed plus 14x squared minus 8. Now, what I would probably do, I mean, I don't have to, but I might to factor out a 2 because they're all even, but let's just leave it that way. Let's just go right to our, calculator or some technology device and plug that in and see if we can find any possible real solutions. So again, let's share the application again. Just gotta move this around just a tad. Okay, let me get rid of this one and put y equal to 2x to the 4th x to the 4th, excuse me, minus 10x cubed plus 14x squared subtracting 8. Now we got to start to see some things here. Let's zoom in a little bit over here. This one over here, that's not a nice integer value, so there's something different going on. Let's zoom in a little bit over here so we can kind of see what's happening. This is where some interesting features take place. Notice I have a 0 over here. That again is one of those decimal numbers, so it's going to have some radicals in it. It's not imaginary numbers. Notice what happens here. The graph is just touching at the point x is equal to 2. So I can see I get a repeated root of x, equal to 2 over here. That gives me 2 zeros here. I get one more 0 over here, 3, and there is one more 0 over here. So there are 4 real zeros. I don't have any complex zeros in this at all. But what I do know is that x minus 2 is a 0. So let's go back to this now. So from that picture, since I just touched the axis, I know it has to be a repeated 0. Now it could either be 2 or 4. I know it's not 4 because the graph crosses at 2 other locations. It has a maximum of 4 zeros. I have a repeated 0 of x equal to 2. So from the graph, I see x equal to 2 is a repeated 0, repeated root. So this tells me x minus 2 squared is a factor. Meaning, if I multiplied this out, x squared minus 4x plus 4, that will divide into this 4th degree polynomial. Let's do that. And that will then enable me to find the other 2 zeros. So let's take a look at that. So I'm going to take my x squared minus 4x plus 4. I'm going to divide that into this. Now, in this case, what I would probably, since even, I could pull out 2 as a factor if I wanted to. I just have to remember that that 2 is there. So I could actually rewrite this in this form. Just going to make this a little bit easier. The numbers will be a little bit easier. 2x to the 4th minus 5x cubed plus 7x squared minus 4. So that's really what I have to. The 2 I don't have to worry about. So I could actually put, you don't have to, you could put it with the 2, but this is just going to be a little bit easier when I work the numbers. But when I factor it out, I need that 2 to come back. x cubed plus 7x squared minus 4. Okay, let's go through the process. What do I multiply x squared by to get x to the 4th? Well, I multiply that by x squared. Let me put it like this too, like I've been doing. I'm going to put plus 0x minus 4. Put in the missing term over here so we don't get messed up when we're trying to subtract an x term from a constant term. Then I multiply everything here by x squared. So I get x to the 4th minus 4x cubed plus 4x squared, but I am subtracting from what's above. So that becomes a plus 4x squared, so it gives me a minus x cubed, this is 0, and a plus 3x squared, and I can bring down the 0x. And now I look at this and that, I multiply that by a negative x, if you will. So I'll multiply that, and I'll do a different color just so you can kind of see over here. This and that. So I multiply everything by a negative x times x squared minus 4x plus 4. I get a negative x cubed, a positive 4x squared, and then a negative, if you will, 4x. But I'm subtracting that from what's above. This is 3, subtracting 4 gives me a minus x squared plus 4x, and I bring down the negative 4. Okay, then what do I multiply this by? A negative 1 again, and you can see you get the same thing back. So it's a minus x, or minus 1, if you will, because that's this and that. So I multiply by a negative of x squared minus 4x plus 4. And what do I get? I get an x squared plus 4x plus 4. Right. Minus 4. Cancel that. And minus 4. And then I'm subtracting everything over here. And I get 0 remainder, which I should. Meaning those are factors. They divide into it evenly. So I can rewrite my polynomial over here in this fashion. The 2 has to be there. I need that 2. That's part of my solution over here. So it's equal to 2 times x minus 2 squared. That's what I'm dividing by, which is x squared minus 4x. Equals to 2 times x minus 2 quantity squared times what's left over there. X squared minus x minus 1. Now this I can't factor, but what I can do is I can actually, if I want, that's an irreducible quadratic. Again, that's what we've been calling our irreducible quadratic. But we still want to find those other zeros. So how can I do that? Quadratic formula. So do that. Take this, use the quadratic formula, and find the other 2 zeros that we saw on the graph there. So try that. Now do that on your own. Make sure you can find those zeros using the quadratic formula. We're going to leave it in that factored form with a linear binomial factor raised to a power and an irreducible quadratic. It means I can't factor it over the integer values or even the rational number values. It has to be factored over, in this case, complex conjugates, or not complex, I mean conjugates and radicals and all these other things. So what are the other zeros? Those are 2 remaining zeros. It's 4th degree. I found one that's repeated twice, so there's 2 more zeros. Remaining zeros. So I get x is equal to the negative of b squared minus 4ac all over 2a. So it's equal to 1 plus the square root of 5 over 2, and 1 minus the square root of 5 over 2. So those are all my zeros, that and x equal to 2. And if we plug that into our calculator, we'll see that's exactly the value, the rounded to the thousands place that we were getting from Desmos. Or even if you set up so you get the same sort of thing. So remember this value over here, we got this one, negative 0.618. So let's plug that in over here and see what we get. So we take 1 minus square root of 5 divided by 2. And there it is, minus 0.618. And it keeps going now. And the other one obviously would be 1 plus. Be the same thing over here, but it's plus. And that's what we have. That other zero over here, you can see it's 1.618. So these are the approximations. What I presented over there are the exact values. And I was able to analyze that fourth degree polynomial. And we did it with a number of things. We did it by, long division, looking at it, the fundamental theorem of algebra guiding us, telling us how many roots to look for, what should their form be in. We got our irreducible quadratic, so we could simply factor that. Okay. Yes, Ashley.
Professor, I have 2 questions for you. All these, like on the homework, we are always graphing it, trying to get one real zero, and then taking it from there? Is that what the steps we should be doing?
That's the approach. Yeah, that's the approach. The traditional way of doing it, you would go through something called the rational zeros theorem. And that would give you, it could give you, depending on the factors of these things, it could give you 20 things to try by using, and they would typically use synthetic division to try. To me, that's an archaic way because that was needed 100 years ago without technology. That was their technology at the time. So why don't we use our technology at the time? We can visually see these things, so find out if it has a real zero. Now, there, in that case, for the fourth degree, it just touched the axis. So that gives me information that I know that I went back. If a zero just touches the axis, then it's raised to an even power. Now, if it crosses through, it could be an odd degree exponent. It could be, for example, in some pictures to look like this. So say here's my x-axis. And you might have a zero that goes just like this. If it just goes like that, then that zero is just raised to the first power, x minus x0 to the first power. If, however, it looks something like this, it kind of comes out and there's a little bit of twisting happening over here. This could be x minus x1. It could be to the third power. It could be the fifth power, seventh power. Usually, if it doesn't go straight through, it's a higher odd exponent. And that's what we learn by visually looking at the graph. And that gives us an indication, especially if they're very high degree polynomials. But when they just touch, over here, as we just saw, and they could touch going that way, or they could touch going this way. Touching this way, it could be my x minus x2, I'll call this x2, this is my x0, and this over here is my x1. Then in this case, it could be a 2, it could be a 4, it could be a 6, it could be an even exponent. And that's how we know just by looking at the graph. It's very telltale about how we're hoping to analyze this. But use technology, because using that technology, the old technology was the rational zeros theorem and Descartes' rule of signs and synthetic division. Synthetic division is just a quick way of determining the value of the polynomial at the function. And if you get 0, we know it's a root, so we don't have to evaluate it. There's so much else to cover, and that takes a lot of work and a lot of time to do that. In this course, there's so much else to cover. Let's use technology, and you'll see. Because on all your tests here at the college, you can use your calculators. Okay, so let's take a look at another one over here. This is an easy one, and this kind of tells you how to focus. So you got to approach this from a different set of perspectives. There's all these different tools you now have, and how can I bring them to bear on a problem? And that's the focus of how do I solve this with everything I know? How do I continue on? Let's take a look at another one. Number 6. Hopefully you start to see a pattern over here. They're all slightly different, and we do different things for each of them. F of x is equal to x to the 6 minus 26x to the 4th plus 5x cubed. Now, how would I start approaching this? Well, I might go to the graph, but I notice here factoring is always good. So the first thing I would do is let's factor in x cubed out of everything. This tells me 3 of the zeros. So what I know is this thing is going to pass through the origin. X equal to 0 is a 0 of this polynomial, and it has multiplicity 3. Okay, so now I need to focus on this. Well, let's kind of just put this in. Well, let's put everything in, and then you'll see what happens here. Let's put the whole thing in, but I could, if I wanted to, just put this in and see if I could find any of its real zeros. 6, 4, 3. So this should be, there we go. Keep me awake there. Otherwise I'd mess it up. So I have my x to the 6, x to the 4th, x cubed. That should be an x, and that definitely is an x cubed over there. Double check. Yeah, okay. So let's plug this whole thing in, the original one. It might be a good idea to always plug the original one so you don't make a mistake going over here. And see what we get. Try it on your calculators. Try it on using your Desmos. But since we're online and we're using a lockdown browser, we can't really use Desmos. When I get this in the radio class, I'll have students using their smartphones with some modifications, so you'll be able to use something like this, a smartphone app for Desmos. So I'm going to put the entire thing in. Y equal to x to the 6 minus 26x to the 4th plus 5x cubed. Now, let's zoom in over here, and exactly what happens is happening over here. This crosses, but you see it doesn't cross straight through. So when it doesn't cross straight through, it's a higher degree. At 0 over here, it does, expand that. Let me just kind of do this zooming in. I'm going to do it a little bit with my tools, a little bit differently. So I'm going to let the y-axis go from I mean, zoom it in some more so you can kind of see what's happening. See how it kind of just barely touches it? If it went straight through, I would know it's the first power. Since it just kind of comes up and then does it, I know it's a high power, so it's the third power. So that's my repeated 0, if you will. Now let's take a look at the other 0 over here. Here's 1 over here. Here's another real 0. Now this one is a hard one to find, so let's see if I can. 3, and there's my 4th root. Let's see if I can zoom out some more now. Zoom out. So here's my default zone over here. So I see there's a lot of activity going on here, and then I have another one over here. That one's easy. That's 5. This one I don't really know, but I know 5 is a real 0. So let's count the zeros I have. Here's 1, 2. At 0 I had 3, so that's 3, 4, 5. And 1, 2, 5, and then I have one more 0 in here, which you can kind of see. That's not the 0. The 0 is right here, that one. That's not 0. Okay, so now I've kind of examined it a little bit. I have a little bit more knowledge. I know how to approach it. So x equal to 5 is a real 0. So in this, I know x equal to 5 is a real 0. So that's what I'm finding. X equal to 5 is also a 0. So what can I do? Let's take this and divide by the factor. That means x minus 5 is a factor. That's a 0, so x minus 5 is a factor. So let's use that to simplify this. I'm going to take this and divide it by x minus 5. So take x minus 5 and divide into that x cubed minus 26x. Well, let's put it this way. I'm going to put a 0x squared just to do that. 0x squared minus 26x plus 5. I want to make sure I line everything up. Practice that. You take it through. Do that long division and tell me what you get. I want you to try that. I'll give you a couple of minutes to try that, or a minute or so to try that. Plug that in and tell me what you get. Because we're kind of analyze this thing, we're going to break it down into manageable pieces. So practice your long division. It's a nice little tool, and you'll use it throughout your higher level math courses. It will come up time and time again when you least expect it. You think, well, you go a long time without using it, and all of a sudden it's there. You have to use it again. And you'll be happy if you learn how to use it and how to recognize when to use it. It'll help you out a lot along the way. That's no, it was a factor. I get a 0 remainder, so I know. If I don't get a 0, you made a mistake because you saw it visually on your computer screen. Okay, so we're slowly enabling ourselves to factor this thing. So what do we have over here? So widget looks like that. Let me get rid of this over here. And we're able to factor this a little bit further. This is equal to x cubed. This factors into x minus 5, and what's left over is the irreducible quadratic. So I'll take this over here and place that as an x squared plus 5x minus 1. I will not be able to factor this over the integers. So that's my factored form. But I'm not done yet because I want to find those zeros. But I can easily find them. So here's my factored form of that 6-degree polynomial function. But let's find the zeros. That's a quadratic. Use the quadratic formula. So the two remaining zeros are the zeros of that irreducible quadratic. So I say x is equal to the negative of b plus or minus the square root of b squared minus 4ac. So it gives me plus 4 over 2a. So it's equal to a negative 5 plus or minus the square root of 29 over 2. So I have two extra zeros. So here are the zeros of the polynomial. So x equal to 0 with a multiplicity of 3, x equal to 5 with a multiplicity of 1, and then these two zeros. X is equal to negative 5 plus the square root of 29 over 2, and that just has multiplicity 1, and x is equal to negative 5 minus the square root of 29 over 2, and that also has multiplicity 1. Now let's just check these out. See, do they agree with what we just got on our graph? It's nice because we have that. Let's plug it into the calculator and see what we get. If I go back to my Desmos, and come over here, let's just plug in that one. So it's equal to a negative 5 plus square root 29. And divide that by 2. And then I get 0.198. So let's take a look at that. Over here, we got that value over here. There it is, 19258 rounds up to 26. That's 26. And then if I look at the other one, and just change this as a minus over here, I just cut and pasted that into there. And then what do I get? Let's take a look at the other one that we zoom out now. Let's go to the default zoom and take a look at this value over here. Negative 5.193, which is exactly that same rounded to the thousands place over here. So this gives me confidence that what I've done here is totally correct. But hopefully you see the process over here. My objective is to get it down to an irreducible quadratic. That will contain my complex roots, if they are there, or my radical roots, if they are there. Okay, let's try another one. Let me give you one to try now. If you can kind of pull this together, we'll have you try number 8 as well as some of the ones on the homework, and I'll go through it as well. But using your technology, either your calculator or an app on the computer, can really give you the necessary insight to do what you had to do. Where in the old days it was a very tedious process, now it becomes a lot quicker. Yes, Joanna? Question, Joanna? Okay, let's kind of look at number 8 and see if you guys can handle this one. Put it up here, and then how would you approach this? It's very similar to what you just saw in 6. So we have my x to the 5th minus x to the 4th minus 12x cubed. So I want two different things. I want all the real zeros and their multiplicities, and I also want the factored form of that. And see if you can kind of do this. This one's a little bit easier to do. Doesn't require a quadratic formula. This one's much easier. So they come in different ways. This is a much easier one. Hopefully you'll see that. And then give me the factored form and the zeros. That was an easy one. Didn't even have to use the quadratic formula. I was able to do this in my head just by looking at it without even having to go to a calculator or a computer. Because I did the first step, and then I recognized, that's a factorable quadratic. So I was done. Didn't even have to go to the computer or calculator. Does anyone want to see that? Yes, Colin.
I'd like to see that. I have no idea how you did that.
Okay, so the first step I always look at is I have variables and everything. So let's factor that x cubed out of everything. This is equal to the x cubed comes to the front. That gives me x squared minus x minus 12. Well, you may remember from your algebra that that's a factorable quadratic. That's x cubed, and that factors, two factors that are binomials. They multiply to negative 12, and they add up to a negative 1. Well, that's just negative 4, positive 3. So there's my 0, x equal to 0 with multiplicity 3. X equal to positive 4, keep me awake. That's why I switch it over here in my head. X is positive 4 with multiplicity 1, and x is negative 3. It's always the opposite sign here with multiplicity 1. So I didn't really have to do much. Very easy, because I know I'm looking for 5 zeros, so 3, 4, 5. One of them happens to be a repeated 0. So if you can factor anything at the beginning, always do that. Because then it makes what you have to deal with after that fact a lot easier to deal with. Because this, I could simply go right into the factoring. Now, if this was an irreducible quadratic, then I could have, I would just left it like this. But if it was something like that, I would have to, like this was a plus 12, then that would be irreducible quadratic. I wouldn't be able to factor it like this. I'd have it this times that, and then I'd have to get these other two remaining zeros using the quadratic formula. Okay, that turned out to be a nice, easy one. Let's try one more over here. Again, have you try it. Hopefully you start to get a little bit better. The more you work, just like anything, the more times you do something, the better you get at it. It's actually physically working the problems and working them out that is so critical and important over here. So 12. This is our number 12. So you have my f of x is equal to a minus x to the fourth minus 4x cubed plus 3x squared plus 16x plus 4. Now, we are looking for 4 zeros. It's a fourth degree polynomial. We're looking for 4 zeros. We know that from the fundamental theorem of algebra. First step might be to kind of look and see, can we find, does this have any real zeros? It may not have any real zeros. It could be that this, and then it's going to be really hard for us to find and to work it out. I won't lie to you, there are certain cases that this approach does not work very well with, Now, that's where you could go to the rational zeros theorem and actually get it, but that's so rare that, if it's a rational zero, you're going to see it on the calculator. It'll give you that. It might give you, like, for 2/3, it might give you 0.666 and then minus 7, and then you kind of guess what's happening. Let's just plug this into the calculator. There's nothing I can do over here other than just plug that into it. Plug that in, do your thing, and I'll do mine over here. I'll share it with you in a second. So you work on that. And then I'll set it up over here to what you should be experiencing. hopefully you can see a quick pattern over there. Hopefully you see right away the following will come into play. Everything is a multiplicity one. It has 4 real zeros, as you can see from the. Those are the factors. And that means the product of those is also a factor. That's also a factor. So as a hint, I want to find those other 2 radical factors. This is what I'd be doing over here. I think mistake here is something like that. Ah. Oh. That's my mistake. Little typo over here. Gotta be careful what I'm doing over here. This one I'm doing. There we go. Yeah, there it goes. No, that's good, 0 there. And I'll show you the picture and how it decided me. And now I'm almost done. Let's see who's talking. Yes, Ashley, you have a question?
Yes, so I graphed that and I messed up and I didn't see the -2 where it passed through. I just saw the +2. So then I started to write like I was just like jumping ahead, seeing if I could do it on my own. I was started to write long division with like a x.
That's fine.
Plus
You can
2.
do this in stages. Yes, you can do this in stages. You don't have to. I could have done with positive 2, and then I would have went from a 4th degree down to a cubic. And then I could have graphed that cubic, and then I might have noticed x is equal to, a negative 2. So x plus 2, I don't have to do this at once. I could first do x plus 2 or x minus 2. Then instead of getting a quadratic, I'd have a cubic. And then I might graph that cubic and say, oh, x minus or x plus 2 is also a factor. This is negative 2 and then positive 2. Yeah, I just did it all at once because I saw it, but you don't have to. For example, let's show you that. While I have this, let me put it on the side over here. So I have my x plus 2, x minus 2, and my irreducible quadratic. I'm going to pull I'll put it over here, minus x squared minus 4x plus 1. There's my irreducible quadratic. But let's say, as you suggested, you did not notice that both of them were solutions. So I could have went this way. It doesn't matter, you said you didn't notice negative 2, so you did x, say you did x minus 2 as a factor. So I go through the same process over here. So this is going to give me an x cubed, or 4x cubed, x cubed, excuse me. So I do my x cubed times x minus 2. So it gives me a x to the 4th minus 2x cubed. And I subtract, so that goes out, that's positive 2, so it gives me a negative 2x cubed. Bring down the 3x squared, so negative 2x squared. So do that. Negative 2x squared times x minus 2 gives me a negative 2x cubed plus a positive 4x squared. When I subtract, I get a negative x squared. Bring down the 16x. And then over here, just a minus x. So it gives me a negative x times x minus 2. So it gives me a negative x squared and a positive 2x. So I'm subtracting over here. So that just brings me, in this case, if I didn't do anything correctly, I should have had 14 and a 4. That's not quite right.
I'm pretty sure it's negative.
Which one? There's negative?
Like in the top, it's supposed to be negative x.
In the top, negative 2, but x cubed minus 2, x was, right? Subtract negative 4, negative 2. But did I write something different? 3 plus 16. Should be okay over here. So I have my negative 2 x squared. Positive 4, subtracting. There's some other, I don't know what am I doing? 3x squared, 16x plus 4. Okay, let's go through it again. Minus 2x cubed. Let's see which one it said. Minus x cubed. Right, yeah, that's my mistake. Put it in red so we can kind of see that, because we wanted to get the same. So negative x cubed, right. So that would give me my negative x cubed, so I get my negative x to the 4th and a positive 2x cubed. So when I subtract, that goes out, that becomes the negative 6 x cubed, bring down to 3x. Okay, then we'll carry it through there. That's a negative 4, and I'm subtracting over here. I get the double negatives, that becomes a negative 4 minus a positive 2, so that's 6. And then I got to put a negative 6 over here. And I get my negative 6x cubed plus 12x squared. Subtracting that, I end up with a negative 9x squared plus 16x. So negative 9x plus 18, yeah, so like negative 9x squared plus 18x, but I'm subtracting, so it gives me a negative 2x plus 4, so it gives me a negative 2 over here, negative 2x plus 4, and I subtract, I get 0. So now I know that's correct. So I'm down to this. So what I might do is I might put this back into my calculator. Let me show you the original one. We're not done yet, but let me show you the original one that we would have gotten. When I plugged it in, this is what I got. This is what I got in Desmos originally. And I could see my 1, 2, 3, 4 zeros. So I saw them, and I saw one was at 2, the other one was at negative 2, and then these two require, they're my radicals. Okay, so let's plug in the new one we got now. Y is equal to minus x cubed minus 6x squared minus 9x minus 2. Notice it goes to the other 3 zeros, as it should. And that's where I might notice, oh, x minus 2 is a factor. Okay, let's utilize that now. So x, x plus 2 is a factor, because x equal to negative 2 is a root. So now I would have this. What I would probably do, notice these are all negatives. To make life a little bit easier for myself, I'd write them all as positive, and then I'd factor that. You can see where they can get cumbersome. But you can do this one at a time if you don't recognize the other thing I just showed you. So what do I put in here? This is going to be an x plus 2. This x equal to negative 2 is a 0. And I'm going to pull out that negative. So I'm just going to write that as x cubed plus 6x squared plus 9x plus 2. Meaning I could have pulled the negative out of that as well. Pull the two as the front. Okay, so now I do the same thing. And now I should get a 0 remainder for this. So when I do that same process, I'm going to multiply that times x squared plus x cubed plus 2x squared, but I subtract. It gives me 4x squared, bring down the 9x, so plus 4x squared plus 8x, but I'm subtracting, so it gives me 1x plus 2 plus 1, x plus 2, I get 0 when I subtract. Okay, so now I was able to bring it down even further. So now I've gotten the following. I think there's a little typo over there. Minus. The other one, I think I should have had a minus here. I didn't do that correctly. This looks okay. Unless the last one, no, the last one was okay, right? I erased it, but this is coming out a little bit different over here. That should be a negative the way I did it. But anyway, you get a 0 remainder. If I do that, that's correct. So this might be a negative over here. I may have messed up on my original one, meaning that whole negative could be factored out. So what I've done, I'm down to this one. Let's use this one and see if that's okay. Let's double check. The way I might double check, I'm kind of going through quickly. I can put that quadratic in. Let's put the quadratic in and see what we get over here. I'll just overlay right on the screen over here. And now if I put in the quadratic over here, I get y equal to x squared plus 4x plus 1. X squared plus 4x plus 1. Yep, the two zeros go right where they were supposed to be. They're kind of going right over everything else. So my first problem here was a mistake. It should have been a negative there. And I can find those. There's the decimal approximations to those two zeros. Well, let's go through and find them exactly now. So when I first set this up, my last original problem should have been a -1. So it kind of shows you where your mistakes are. So the other one, I pulled out the negative. So I pulled out the negative, x plus 2 x minus 2, and then this gives me x squared plus 4x plus 1. Meaning I pulled out this negative to the front. Now I can use to find what the roots are, I can simply use the quadratic formula. So again, if you don't see the double root there, it's okay. You can do it piece by piece and then go back and reanalyze it. You're breaking it down and taking a complicated problem and breaking it into multiple subpieces. So the zeros of that, x is equal to a negative of b plus or minus the square root of b squared, which is 16 minus 4ac all over 2. Now, if you let the negative in there, it would give you the same answer. It's just easy to work with everything being all positive. So x is equal to negative 4 plus or minus the square root of 12 over 2, which is equal to negative 4 plus or minus. That comes out as 2 square roots of 3 over 2, which is equal to a negative 2 plus or minus the square root of 3. And those are my other real zeros. I'll just do that, and then that should agree with what I had up on my board there in Blackboard. Let's put, in Desmos. Let's see what we have over here. So if I come over, put those two zeros in, so I put a negative 2 plus square root of 3. And that's one over here, minus 2.268. You can see that's exactly it. And then the other one as well, negative 2 minus the square root of 3. And that will give my other 0 over here. Let's just turn these off and go back to our original function so you can see that one over here I just got minus 0.268. Minus 3732, and the other two that we found early on. And those are 4 real zeros that we have. 2 that we can show approximately here, but I want the exact values so we can kind of show those exactly over here. So the other zeros are x is equal to negative 2 plus the square root of 3, and x is equal to negative 2 minus the square root of 3. And there we go. We have all the zeros, they're all real, and we have the factored form of that. 2 linear factors and 1 irreducible quadratics. Now I could factor this quadratic, but it just looks messy. If I were to, I don't want to get to the idea that you can't factor that. It factors into a messy looking thing. This is what this would factor into. This would factor into x plus 2 minus the square root of 3 times x plus 2 plus the square root of 3. So that's what this factors into. And you can kind of see what's happened over here. You'll see exactly what happened. This will be 4 minus 3, which will give me 1 over here. The middle terms, most of them will cancel out. The radicals will cancel out, but the 2x and the 2x will give me 4x. So you can factor it, but we say it's irreducible because of the radical over here. It's not factorable over the integer values, meaning integer coefficients throughout. That's a radical coefficient. Now, if I multiply this out, I would indeed get that back. But we don't factor it, we just leave it in that form as opposed to this. But you could theoretically factor it if you wanted to. And this would then, fundamental theorem of algebra would tell you, okay, I can factor it into all linear factors of its roots if I included radicals and complex roots as part of the factorization process. But that's it. Now we have our function in factored form, a very usable form. And we could validate that. You should also maybe want to validate that when you come back over here. Let me just show you as we're ending what we have here. Let's validate what we just seem to have found over here. So let me get rid of this, 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 and this, and now plug in my factored form. So y equals to the negative of x plus 2, x minus 2, and then my irreducible quadratic, x squared plus 4x plus 1. Now let's change the color so we can see that there is a different color on this one. Let's change that color. I'll make that black. So if I shut this off, you can see it's the same identical function. One is multiplied out, the other one is in factored form. So in the end, your factored form should fall right on top of. Now if I had not put this negative over here, it would flip the graph. If I made that, positive, I get the flip graph of that. Has the same zeros, it does not have the same shape or factored form, but the zeros are identical. But when I put that back, it goes back to what I would anticipate it to be. Okay, so we covered quite a bit today in just showing you how to analyze this. That's the whole purpose of the fundamental theorem of algebra. We want to learn as much about these functions as we can. The zeros are important. They will tell us a lot of information. When you get to the calculus, you'll look at the picture and you'll have a better understanding. The zeros of these are always the x-intercepts, if they're real. If they're not real, we didn't see any. If they were, some of them might turn out to give you complex zeros. So we might write, minus 2 plus square root of 3i, minus 2 minus the square root of 3i. In that case, the graph will not touch the x-axis only at the two. If it occurs that this happened to be complex, it would only touch it twice, not 4 times like it did there. Some of the other ones, the odd answered ones, will probably fall into that category. Okay, so that's pretty much all I wanted to kind of go over today, just kind of show you something. Now, if you, for example, let's say my zeros turned out to be this. Very similar to the other one, but let's say, I'll go back to this picture here. Kind of say it in a different way. I'm going to go back to our decimal, so I'm going to change it ever so slightly over here. And let's say I turn around and let me just do something quick calculation over here. I think it's that's x squared. Let me just change this to x squared plus 2x plus 2. Now this is still a 4th degree polynomial over here, but notice it only passes through 2 places over here. So you can see that I only have 2 real crossings, or real zeros, if you will, of the function. Because this function, x squared plus 2x plus 2, factors into the following. So if I use that, and if I were to factor my x squared plus 2x plus 2, I can't factor that. So what do? I use my quadratic formula. X is equal to the negative of b plus or minus b squared minus 4ac over 2. So x then, negative 2 plus or minus square root of negative 4 over 2. So x is equal to, in this case, minus 2 plus or minus 2i over 2, which is equal to negative 1 plus or minus I. That has complex zeros. In that case, you will not cross the x-axis because we're only graphing the real. I put an interesting link that some person explored, that if you were to graph these parabolas in this complex plane in another three-dimensional way, you can actually see where these would, cross over at one plus or minus I. But that's a little more beyond the focus of this. But that's all it is. If it's fourth degree, has four roots. It could have no root, no real roots at all. It has to, if it has one root, it has to have two. If it has three, it has to have four. They have to occur in conjugate pairs. That's why if you read through the chapter, there's all those little hints about understanding what you have and how it guides you. Okay, so that being said,